that with chains.
Sorry
But
about that.
obviously, I
Okay.
can do all of those in one day. I'm also broke.
So now we're gonna finish up this big long lecture on entropy and all this good stuff. So, when they figured out this idea of entropy and how this is what nature likes a hot mess. It actually, this was done like kind of in the 1800s, and it actually influenced like the culture of Europe. And you think, well, what does this have to do with culture of Europe? And it actually influenced culture, it influenced art. Because what they got to thinking about is like, okay, what's the fate of the universe, okay, long term? Obviously not like, hey, what's gonna happen this afternoon? What's gonna be at 11:30? This is like the ultimate fate of the universe. And so they figured out that if you look at how the universe might end up, and again, this is a long time ago. So, you look at how, all right, our star, for example, our star works by taking hydrogen, fusing it into helium. It has a finite amount of hydrogen, okay? And then once that hydrogen runs out, the star is going to go dark. And so that's what we kind of figured out. It's like, what's the ultimate fate of the universe? Is it just going to go cold and dark? And that's the ultimate long-term fate. Is that eventually, when you look at the night sky, you're not going to see stars, okay? Because of the fact that the stars are going to run out of fuel. And if you look at this idea of conservation of energy, okay, which is also fits with the idea of conservation of mass from Einstein's equation, E equals mc squared. The universe began with a certain finite amount of energy and mass. And what the first generations of stars did is that you had pure energy, it cooled down, and then mass began to form, you began stars, hey, hydrogen began to fuse. In the first generations of stars, they collapsed, they exploded. You made the heavier elements. Eventually you got into neutron stars, they collapsed, exploded. That's how you get like the really heavy elements like gold and the silver and that type of thing, because those couldn't have come from the first or second generations of stars. And so eventually all of the stars are going to run out of fuel. And eventually the universe is just going to go, you're going to see stars begin to just fade out, okay? And so once they realize that, it's just like, oh, that's just kind of depressing. That eventually the universe is going to run out of fuel. And so it actually influenced the literature, it influenced the art. Everything kind of took a dark turn in all of those aspects. So this isn't just, oh, here's a random idea. Like, this influences what is going to happen in the universe. So,
Bless you.
you okay?
I didn't take my allergy medicine.
Okay. All right. So there's a couple of really, really important ideas. One is this that I have highlighted. Delta S for the surroundings is negative delta H for the system. So here's what this is. This is where you have to think through a process logically. And you say, okay, let's say for a reaction that you know that is negative delta H for a reaction. So there are certain things you have to begin to know without hesitation. If you have negative delta H for the reaction, endothermic or exothermic? Exothermic, okay? So that means energy is going to be given off. So here's the water, here's the air, whatever that is, okay? You blow up a hydrogen balloon, whatever that is. So if it's exothermic, energy is going to be released, which means the surroundings are going to gain this energy, okay? So this is a classic situation where we can't quantifiably measure delta S. But here's what we can do. You all have done labs where you measured delta H. Cool. You calculated that. Okay, we can get that number. Not directly, but we can get that number. And then we realize, oh, okay, so it was negative delta H for the reaction. And there's this lurking negative sign out here, okay, and that's vitally important. It's just like, oh, let's just randomly throw a negative sign on there just for fun. No, here's why this is so important, is that that negative sign then when you combine that with the negative of the negative delta H, makes that a positive delta S to the surroundings. So if you have an exothermic reaction, energy is going to be given off, then we can quantify what's going to happen to the increase in entropy in the surroundings. So if we know that the whatever temperature that's run at, and that temperature has to be in Kelvin, then you can measure and calculate the delta S of the surroundings. When we do a lab next week, where you can actually see this, don't ask me, say, hey, Burkamp, where's the delta S probes, okay? We don't have them. We can't measure Gibbs Free Energy, we can't measure enthalpy, we can't measure entropy. But we can measure the impact that it has on the surroundings, and then we can end up with those values. So, first law of thermodynamics. The universe started with a certain amount of energy and mass, and that's all we got. All we can do is just change the form of it. That's all we got. Now, second law, and these are laws. This isn't just, just on Fridays, on April 18th, this is the only time this applies. Every time else, it's just kind of iffy, okay? No, these are laws, okay? These are very Newton's laws of motions, Kepler's laws of planetary motion, okay? Laws of thermodynamics. So, and again, when we're talking about the universe, we mean the universe. This isn't just Burkamp's room in G20. This isn't your bedroom. This isn't Wichita, Kansas. This is the universe. So there's three options. First off, mathematically, here's what you can add together. The delta S of the system plus delta S of the surroundings. Because you can't talk about either one of those in isolation. Classic example. You're going to melt ice. Okay, ice is the system. You have the surroundings, which is the glass of water, which is the air around it, whatever that might be. So you're going to add those two values together. Now, but again, whatever you lose from one, you gain from the other. These have to have opposite signs. So if you have that chunk of ice, which is going to melt, okay, energy is going to flow into the system. So what's going to happen to the entropy of the ice as it melts? Caption. It's going to increase because it's going from a solid into a liquid. Entropy is going to increase. So melting ice for the system is a positive value because that's going to melt. It's going to go from a solid into a liquid. The surroundings, though, have to give up that energy. So what's going to happen to the delta S of the surroundings? That's going to be a negative value. Okay? So there's three options that can happen when you add this together. If the delta S of the system is bigger than the negative delta S of the surroundings, you get a positive delta S and the reaction becomes spontaneous. Okay? So any spontaneous reaction, you're going to increase the entropy of the universe. The other option is that delta S for the universe could be a negative value. So if the delta S for the system is a positive value, but it's smaller than the negative value for the surroundings, it's not going to happen. Now, it could happen if you dump energy into the system, just like anything. Hey, if it's not spontaneous in one direction, hey, you hook it up to an energy source. Maybe then we can make it happen. Now, the other option is that delta S in the universe can just be equal to zero. In that situation, the system is in equilibrium. So that's what happens when you have things that are temperature dependent. Melting ice, boiling water, okay? Anything that goes through a phase change, you can reach a point where delta S is zero and the system's in equilibrium. So you have three options for delta S for the universe. Positive, hey, Mother Nature likes it, because what you'll see is that Mother Nature likes a hot mess. Delta S is negative, oh, that's cold. Okay, we'll get into why that's cold later on. Mother Nature goes, not digging it. Or Mother Nature goes, it's zero, I'm just going to chill out, hey, do whatever, I'm in equilibrium. Okay, so those are only your three options. Positive, it's going to happen. Zero, it's in equilibrium. Negative, it's not going to happen. in the forward direction. So, this next line is what happens with my room. And I justify by keeping my room in a state of disarray for this line right here, okay? My room is in a state of disarray for this line right here, which says no process that produces an order, lowering the entropy, in a system, which is my room, can proceed without producing an equal or greater amount of disorder in its surroundings. So, let's say I walk in here, it's like, okay, even by my standards, my room is out of control, okay? So it's supposed to rain tomorrow, Sunday, like I can't work out on the ranch, might as well come in here and clean. So I'm gonna start gathering stuff up, making nice little piles, okay? Putting stuff away, maybe even dust. So the room is the system. But by me cleaning, I'm actually increasing the disorder. And you're going, well, what do you mean? You're hiding stuff up. But if you think about it, by me being in the room, my body is giving off thermal energy, okay? Every one of us is a little furnace, okay? On a cellular level, we produce energy, okay? Which is a cool thing. And our byproducts are carbon dioxide and water vapor and heat. So I'm gonna be in the room, okay? My body's gonna be giving off thermal energy. So the surrounding air around me, my body temperature is say 96 degrees, the room temperature is 72 degrees. So the air around me is gonna get a little bit warmer, okay? Not noticeable, okay, but it's gonna get a little bit warmer. I move through the room. I disturb the air, okay? That's gonna create a increase in entropy in the room because I'm gonna be moving through the room, okay? Be giving off energy. There's gonna be, I'm gonna make sounds. My room is very squeaky, okay? You all heard the squeaky floor, okay? There's gonna be sound energy that's gonna be there. So, yes, I am going to decrease the entropy in the room. But, as far as the room being a system, but by doing that, I'm also increasing the entropy of the surroundings. So, Easter weekend, let's say you're having family over, parental units go, hey, you need to clean your room. It's like, hey, if I do that, just fair warning, I'm going to increase the entropy of surroundings. Your room's going to look clean, but know this, I'm also going to increase the entropy. Okay? Homework installed. So, we're going to start to look at some examples. So, you let something sit out, a piece of iron sit out in the rain, okay, and it rusts. So, at its core level, iron reacts with oxygen in the air, and you make iron oxide, okay? That's the simple version of rust, okay? Now, one of the things that you've got to be able to do is, did we start that camera?
Yeah.
Okay, good, just check. Because I don't,
Yeah,
Cohen,
we're good.
bless his heart, comes in. Do I, and I gave him like the assignment and these notes that I'm gonna give you guys. And he goes, Cohen, yeah, I'm gonna roll you under the bus. That's assuming you ever watch this. And he goes,
He won't.
It's a poet.
He
I
won't.
know.
He doesn't watch these.
And he said, am I gonna learn anything from the lecture today that's gonna help me on this assignment? I was like, just think this through. Seriously.
You could have asked that.
Did you have to ask the question? It's like, no, you don't have to learn anything today. Here's the assignment. You can just figure it out on your own. It's like, God. Anyway.
He's pretty stupid.
Well, he's not. But he just
You don't know
doesn't
him.
think. Okay, so one of the things that you can look at to determine the sign of, listen to me, the change in entropy. A simple way to look at it is to look at how many moles of gas there are as reactants versus how many moles of gas there are as products, okay? So if you look at what happens to make rust, you have elemental iron, okay? And then you've got all of this oxygen bopping around, okay? Gases have tremendously high entropy, okay? They're bouncing around, always like, okay, which is a cool thing, because if gases didn't have entropy, we wouldn't have pressure. So gases have pressure because they have entropy. If gases didn't have entropy, they would all line up in a neat row, and then that would be bad, because then they wouldn't be moving around. So if you look at what happens, I'm going to start off with 4 moles of iron. I'm going to have 3 moles of oxygen bopping around. But then I'm going to end up with rust. So what do you think happened to the entropy comparing the products to the reactants? Which do you think has more entropy? The reactants or the products?
Reactant.
Why 1G?
Because there's gas, and there's no gas.
Ah!
Yes.
Beautiful.
Thank you.
Okay? So I go from having 3 moles of oxygen, crazy, bopping around, woo! Okay? And then all of a sudden this oxygen is going to react with the oxygen, the oxygen is going to react with the iron, and it's like, let's simmer down, people. Okay? So instead of this oxygen running around crazy, now it's going to get bound up with that oxygen. Entropy is going to go down. So here's a simple way to predict entropy. It's not always true, but it is for the most part. If you compare the moles of reactant to the moles of product, if there are more moles of gaseous reactant than there are product, entropy is going to decrease. If you increase the number of moles of gas in the reaction, entropy is going to increase. So if you increase the number of moles of gas, you increase entropy. If you decrease the number of moles of gas, you decrease entropy. Okay? Basic idea. So, we know this is a spontaneous reaction. Things rust. Okay? It happens. So you know this is a spontaneous reaction. We don't have to hook it up to a machine. We don't have to have an outside energy source. Things rust. So we know this is spontaneous. So I know that I'm going to have an increase in the entropy of the universe. But what happens is that my delta S for the system and delta S for the surroundings, okay, when I add those two values together, if I get that spontaneous reaction, that means that one value has to be bigger than the other. So in this situation, delta S is negative because I'm decreasing the number of moles of gas. That's why that's a negative value. So that means the surroundings for this to be a spontaneous reaction has to be a positive value bigger than the negative value of the system. Broad idea. Now, this is how this plays out. If you said, all right, we're going to lose all thermodynamic equations, and we have to start over with one equation. This is the one I guarantee you people would pick. And it's delta G equals delta H minus T delta S. Okay? So this is your Gibbs Free Energy. We've talked about this. Delta H is your enthalpy. T is your temperature. What units do you think the temperature has to be in? Kelvin. Absolutely, absolutely, absolutely. I cannot emphasize this enough. The temperature has to be in Kelvin. And this is your change in entropy. All right. So this is probably literally, if you said we're going to lose everything that we know about thermodynamics, but we get to keep one equation, this is the one that I would recommend that we keep. Because this will tell us if the system can be in equilibrium, if there's going to be phase change, if the reaction is going to happen, if the reaction is not going to happen. Is it spontaneous? Is it not spontaneous? So it looks like a fairly simple equation. But there's a tremendous amount of complexity hidden within this. Now, so there are going to be 4 different scenarios that we can look at, okay? So here's your 4 possible combinations. You can have a negative delta H, and you can have a positive delta S. You could have a negative delta H with a negative delta S. You could have a positive delta H with negative delta S. And you could have a positive delta H with positive delta S. Okay? So these are the 4 combinations that you can have. And based upon these values, you're going to get reactions that are always spontaneous. You're going to get reactions that are never spontaneous. Some that are dependent upon low temperatures and some that are dependent upon high temperatures. So Kevin, stop you on the camera. I need to hand out some notes.